Hello there. The topic I'm presenting today is on perovskite solar cells. The term perovskite might be foreign to you, but they are at the forefront of solar cell research with tremendous potential. In the following slides, I will seek to explain what are perovskites and how they may be potentially found on rooftops of Singapore buildings in the near future. For a head start, why harvest solar energy? Well, we are increasingly vulnerable to the catastrophic effects of climate change. Solar energy is a clean and renewable source of energy. Here in Singapore, it's the most viable option, and the government sees a need to ramp up such harvesting towards a clean, affordable, and reliable energy future. Solar energy is harvested by photovoltaic devices, PV in short. These devices absorb light from the sun and converts them into usable electricity. Currently, 98% of the solar panels in the market are made of silicon. They have a power conversion efficiency of 26% and can usually last for about 25 years in typical weather. Over the years, its fabrication cost is decreasing due to an economies of scale from the extensive industrialization in the microelectronics industry. A new material for PV devices would be thus required to be more efficient or of a significantly lower cost, in which perovskites might hold a key to both fronts. Perovskites originate from a natural mineral known as calcium titanate, which was named after Russian mineralogist Lev Perovsky. Alongside similar minerals like magnesium silicate, they form the Earth's lower mantle. These minerals have superconductor properties that strengthens the Earth's magnetic field, which later on brings life to the planet. Scientists are fascinated by these interesting structures, and today, perovskites are materials that have similar structures to that of calcium titanate as illustrated here. Today, the perovskites we use are organic, inorganic halide perovskites. It comprises of a carbon-based organic component that renders the perovskite good solubility and also facilitates self-assembly. The inorganic component is metal-based, such as lead or tin, and it provides precise crystalline structures from its extensive network of interactions. The first perovskite solar cell was innovated by Japanese engineer Miyasaka and colleagues in 2009 with a PCE of 3.8%. This garnered much attention, and in 11 years, perovskites today are compatible with various cell architectures and also exhibit an efficiency ranging from 18 to 24%, surpassing existing technologies. This is very impressive in comparison with silicon PVs, where the first cell is made in 1954 and it now has a PCE of 26%. So, how does a perovskite solar cell work? Firstly, when the perovskite absorbs light from the sun, the electrons take in this energy and dislodges from the perovskite. This causes holes to be left behind, which act like positive charges. The energized electrons are thus able to flow towards the electrodes and through the circuit, generating electrical currents in the process. The perovskite solar cell here is actually easier and cheaper to fabricate as compared to the silicon cell. I will now talk about the fabrication process, which starts off with mixing precursors, lead halide and ammonium halide salts of choice in the solvent. These salts are commercially available and also cheap. Next, this solution was heated up and cooled slowly to remove the solvent. This is followed by spin coating, where we deposit the perovskites on a surface to form a film, which is then completed by sealing the cell. In comparison, the fabrication of silicon solar cells are more energy intensive and requires the use of corrosive hydrochloric acid. In fact, here in SPMS, Prof. Soom printed a perovskite solar cell using a screen printer commonly used in t-shirt printing. These perovskites are printed on flexible plastic films, which can then be used in further applications. The advances in perovskite technology has driven researchers to improve efficiencies beyond current limits, and one approach is the use of multi-junction or tandem solar cells. Individually, silicon solar cells have an efficiency of 26%, while perovskites are in a range of 18 to 24%. However, when we stack them together, they have an efficiency of 28%, and this is due to synergistic absorption, where perovskites absorb lower wavelengths of light such as blue light, while silicon absorbs higher ones such as red light. These tandem cells are far from reaching its potential at 45%, and researchers are working hard towards it. Perovskites are also tunable, where we can change certain aspects such as its dimensionality to obtain interesting and enhanced properties. The following shows how are different dimensions of perovskites structured. Lastly, every exciting new technology have their own challenges, and the first challenge towards the commercialization of perovskites is the reliance on lead. Lead is not only toxic but also environmentally damaging, which precludes the use of perovskites in consumer applications. Other replacements are sourced but come with limited success. Secondly, perovskites are not stable in water and in high temperatures. This is worrying as water is present in rain and water vapor, while the sun can get very hot at times. This degrades the perovskite and decreases its durability and capacity. Thirdly, there are also scaling up problems, as with a larger surface area, there's greater resistivity which blocks some current out and reduces its efficiency. Also, there might be non-uniform coating of perovskite in the film. Last but not least, as this technology is relatively new, there is little long-term studies performed, as we do not know how long they can last out in the field. The industrial standard, which ascertains durability of solar panels for 25 years, are based on silicon cells and not a good indicator for perovskites, as they have different instabilities. There is an instance in which a perovskite passed this test but degrades in just 2 years. Thank you for your kind attention, and I hope you learned something about perovskites.